Let's go. Quick recap of the ones we did so far. Then we'll jump into D. So we're picking up with those continuity examples. So we saw A, f of x equals x squared. That guy we know was pretty nice. That's the parabola that we all know and love. Has to be the origin. We saw this one was continuous everywhere. And you know the graph, so of course you believe it. We actually showed why it was continuous everywhere. We went through the calculations. In the second one, f of x equals x squared minus 4 over x minus 2. We actually graphed something similar to this before, if not exactly this. So pretty much the idea was at 2 it was meaningless because you divided by 0. But for everything else, this actually reduced like a normal fraction and reduced to x plus 2. So it was just a straight line, positive slope, going up like that. Now, if you could draw the picture, as I just did, you could immediately just look at that and realize, oh, it's not continuous at some point. At 2, because there's a hole, remember continuous just means there are no holes, no gaps, no jumps, no anything like that. But at 2, you can see that there would be a hole on this graph. Otherwise though, looks like a straight line. So we saw that this one was continuous on the real line, except at 2. So that was the answer. And I believe that also went through C with you. Now in C, we kind of tried to tweak things a little bit, so we had this function, except we purposefully avoided division by 0, so it's only that definition when your x was not 2, and we made it 0 when x is 2. And if you were to draw a picture of that one, what you'd realize happened. So last time we did the computations here, but I actually want you to now have some sort of visual perspective as to what was actually going on. Now if you actually drew this one, you'll notice that it starts out like that, except for at 2. But at 2, we actually redefined the function to be the output 0. So realize there was an issue here, it wasn't continuous, there's a hole right there. So I guess right here we're trying to fill in the hole, but we did a really bad job of it. You had one jump, and we missed the mark. So we filled in the hole right there. Now, it didn't actually help matters that we filled in the hole right there, because it's not continuous. I still have to lift up my pencil, come down here from this point, and then come in. Okay? Still not continuous. 2 is still not working here in terms of continuity. So this was again continuous on minus infinity to 2 and union 2 to infinity, right? And our calculations showed that without me even having to draw the picture. Like I could figure that out straight from the calculations. This is going to work everywhere, that's not going to work at 2, and that's not going to work at 2. We could actually do calculations and know this. Which leads us to D, which you guys were supposed to try. Maybe someone can tell me how to actually go through this one. So we tried again to change this function. Yeah.
F of 2 equals 4 for step 1.
Okay, so so what is the approach? Remember the question was determine where the functions are continuous. So what is the strategy? What is the approach we do here? Like general approach.
You
Yeah.
have to check like the 3 rules.
You have to check the 3 rules. What are they?
That point is defined.
That the point is defined, which as he said it is, that f of 2 is actually equal to 4.
That the
Well, the
limit
point 2.
exists.
The limit at the point exists.
And that the point and the limit are the same thing.
Right, the output and the limit will give you the same thing. So there are 3 things to check that a function works in the sense that it's continuous at a point. So, like above, I mean, we mentioned this before, so I'm not gonna really go through it again. If x is not equal to 2, we're fine, right? Like 2 was the only real issue that we had here. 2, there was like this threat of division by 0 on the top, so 2 is a problem, right? If we're not at 2, everything is fine, it's just a regular fraction. This is just 4, which is no problem with 4, and that would just be a fraction that you can reduce and compute. No problems at if your x is not 2. So the first thing you would probably say here is if x is not 2, we're fine, don't worry about it. However, there is a potential problem at 2. Now once you start to go in there and examine that, now is when you apply the 3 rules. We're going to say, okay, start with step 1. We have to check 3 things. So if we're not at 2, we're okay. What's going on at 2? Check if the 3 things work out. So now you would check, is f of 2 defined? And then you'd be like, yeah, it's defined. F of 2 is actually equal to 4 by definition of the function. They said when x is 2, the output is 4. So that's what f of 2 is, so it's defined. So the first step works out. That check. 2. Does the limit as we approach 2 exist? Well, we would go in and do that. So we want the limit as we approach 2 of f of x. That's just going to be the limit as we approach 2 of. So looking at the definition, we realize at 2, at that one point, it's 4. Limits don't care about being at the point, so we're going to ignore that part for the limit. The limit's going to care about being close to 2, everyone else around 2. So this top definition is the one that we're going to look for. Now to actually compute that limit, well, there's a whole other list of strategies that we go through in our head. 1, first try to plug it, doesn't work. 2, try to simplify the plug. So then we'll go through here. That would realize the top is a difference of squares. Those would cancel, you get the limit as x approaches 2 of x plus 2. Now you can plug in, get the answer 4. So then the third thing you're going to check is that these are equal. Okay, so these 3 things, what do they allow me to conclude? Yeah.
F is continuous from negative infinity to infinity.
No, these 3 things do not allow me to conclude that. Yeah.
It's continuous from negative infinity, comma 2, union 2, comma infinity.
No. Not allowed to conclude that. What can I conclude from these 3 things? What we can conclude, based on the rules and definitions, is that f is continuous where?
Everywhere but 2.
At 2.
At 2 specifically, right? These 3 bullet points give us that one point, right? How can you make the conclusion that it's going to work everywhere? Well, by also considering this bullet point. Right? Now, at 2, everything works out. We're continuous. It is actually true that the limit as x approaches 2 of f of x gives me the same value as f of 2. That's the definition of continuity at x equals 2.
I have a question.
Yes.
So does that mean for B that it's continuous at everywhere but 2?
Right.
Okay.
So, and that's how we write this. It doesn't work at 2. Right, 2 was excluded here, it's an open parentheses. In this case though, now, you probably don't have to write this, but you can say, since it's continuous at 2, I know it's continuous at 2 because I just showed it was continuous at 2 here. and it's continuous when we're not 2. Now, we didn't actually show it, but I at least mentioned it right here. Those two things together now allows me to continue the conclusion. This means if it's continuous when we're at 2 and it's continuous when we're not at 2, then it's continuous everywhere. It's continuous always. F is continuous on the entire line. So remember, there's a distinction between being continuous at a specific point versus being continuous everywhere. And so whenever you're doing that 3-step process, that is you checking continuity at a specific point, right? That won't tell you about everywhere, right? You actually have to think bigger than that. But you see something like this, 2 was really the only issue you kind of saw coming up because, oh, there's like a division by 2 kind of almost there. If we're not at 2, we're fine. So I know everywhere on the real line, like on this interval, everything is hunky-dory, right? 2 is potentially a problem. I know we tried to fill in at 2, but we've tried that before and they didn't do a good job. So we want to make sure that things were done properly here. So what we do is at 2 specifically, we go through and we check all the points. And this time they actually worked out. Last time they didn't. This time though, they worked out. So because it works at 2, and because it works for not 2, that describes everybody. Everyone's going to be either 2 or not, right? So that tells you, these 2 things tell you that it's continuous everywhere. And you'll notice what happened here, just to continue what we're doing during the picture. So you had your function doing this thing, and at 2 there was a hole. That hole, the location was around 4. We know that because that's what the limit told us, and someone went and filled that in. They filled it in at 4. So now you realize, it's not like the other situation where we didn't fill it in the correct spot. There was a hole and we actually filled it in at the right value by step 1. So now you'll realize that we've created something that's continuous. It's always going to work. I can just keep going now. Like I don't have to jump over that hole, right? That's how I know that it's going to work all the time. It will work everywhere. In fact, this guy is going to look now, it's going to behave exactly like y equals x plus 2. It's always going to work because we filled in the gap. So we've not, we've removed the gap disruption. And this is an example of what's called a removable discontinuity, because you know math people are naming things. So here it was discontinuous at 2 without this, but we now fill that in and now it works. We remove the discontinuity. Don't have to really worry about that though, so I won't really say anything more about that. But okay, so let's do the last example. And this one was x squared plus 5x plus 6 over x plus 2. If x is not minus 2, it's 1 if x equals minus 2. Okay, go from beginning to end. This guy shows up on a test. What do you write down? First thing you write down. Yeah?
At x equals negative 2.
Okay, so you want to look at x equals negative 2?
So you would do f of negative 2 is 1.
F of negative 2 is 1.
And then you want to find the limit of, as x approaches negative 2, of the function.
And that's going to be what?
1.
How do you know? What am I finding the limit of?
Of x squared plus 5x plus 6 over x plus 2. which is equal to 1, if you solve it.
How do you know? Or what do you do?
I simplified the top to x, I factored it to x plus 3 and x plus 2.
X plus
And
3,
then
x plus 2.
Cancel the bottom. You're left with negative 2 plus 3, which is 1 when you plug it in. And then you can conclude the limit is the function is continuous at x equals negative 2.
Okay, so they're equal. And so we can say f is continuous at x equals negative 2. Okay, what else can you say? So is that the only place it's continuous?
Is it also everywhere else but negative 2?
So you also make another bullet point. Otherwise, just like otherwise we're fine. I at least want to know that you thought about it. You considered, if it's not negative 2, is everything else okay? Well, if it's not negative 2, there's no division by 0 happening. Everything seems to check out there. In fact, if it's not negative 2, this guy is going to simplify to x plus 3, which is pretty nice. Everything's fine. 1 is, so we're not even at there. So yeah, if we're not at x plus 2, everything is okay. At x equals minus 2, why you kind of singled this out is because, of course, there was a potential problem. Right? So now you're faced with this question on an exam. I expect you actually look at the question and realize, you know what, there's a division here. Potentially there's a problem if I divide by 0. So x equals minus 2 should actually jump out at you. Okay, there's a potential problem here. Let's see if everything's okay. You go through and you check, is it okay? How do you check? With the 3-point process that I gave you last time. Okay, everything checks out. We're good at minus 2. Okay, cool. Any other problems around? And you look at that and like, no, there are no real other problems. That's a 1. This guy, as long as I'm not dividing by 0, he's going to be fine. It's just a regular old fraction. So at negative 2, we're fine. Otherwise, we're fine. Therefore, you can conclude f is continuous. So that's kind of the thought process. So like if this were like a test and I'm grading your work and I'm trying to see what you should write, I want to give you like full credit for something. A full credit answer would look something like this, right? Where you actually, I can see what you're thinking. I can see that you identified, okay, potential problems are here. Otherwise, we're fine. Specifically dealing with the potential problems, I want you to show that they all check out. And then, okay, we're fine over here, we're fine over here, we're fine everywhere, right? Every now and then, things aren't going to work out over here. And then you're just going to say, okay, it works on this part, but not that part. That's a full answer from beginning to end. And so hopefully that's clear. We know how to verify continuity, actually where something would be continuous. And it's checking with that 3-step process. But again, the 3-step process only works at one point specifically, at one point at a time. So you pretty much identify all the bad points, the potential points. You do the 3-step process for the check. You verify that if we're not at these bad points, everything is fine, and then you're good. Yeah.
Do you happen to have an example of a problem where it's only continuous at that point and like we have to rule out that it's continuous everywhere?
No, because that actually doesn't make any sense in the sense that to be continuous, you actually need at x equals a, you actually need the limit as x approaches a of f of x to be equal to f of a, right? Now what does it mean? what, to exist, x equals a can be isolated. Right, so you'll never have a situation where, you know what, it's gonna work out at this point, but it won't work out anywhere beside it. Like, that's not possible. Because if that were the case, like if I had a graph and it looks like that, and at this one point it's filled in, I can't really approach it with a limit. I can't actually get close in the first place.
Okay.
So it actually wouldn't make sense to say it's continuous at this specific point and nowhere else, right? That's never gonna happen. The moment you're continuous at a point, you're automatically sort of continuous at all points adjacent to it right away. Because otherwise you wouldn't be able to make sense of this in the first place.
Okay.
So you're never gonna end up in a situation where it's only continuous at x equals this value and nowhere else. It's not gonna happen. That's actually not possible. In fact, if you had a function like that, and someone asks you, is it continuous there? The answer would be no. Right? It's continuous over here, it's continuous over here, it's not continuous there. Because that equation doesn't even make sense to talk about. Right? So the most thing that this will identify is like if there's like a hole, like you'll figure that out. If the limit doesn't work, it means that there's a jump. But yeah, you're never gonna have continuity at only one point. You can't actually do that. Because for the limit to even work, you have to be able to get close to it. So adjacent points have to be in play. Once a point is isolated, all bets are off. Something else I want to mention, it's a bit overdue. Sorry should I mentioned it before I started continuity, but I think we're still gonna have reason to use it later on. But I want to talk about the limit properties. We're not done with limits by a long shot, but limit properties. So we've been using a lot of these the whole time, but I want to explicitly write them down so you know what the rules of the games are when it comes to computing limits. Let C be a constant. And suppose we have these two limits. Limit as x approaches a of x equals L. Limit as x approaches a of g of x equals m exists. And so we have two limits, they exist, so these cannot be d and e and are finite. So they all also cannot be infinity, right? So I have two limits and they give us like numbers. Then the following rule. First, it's worth mentioning because sometimes people forget. Limit of a constant is just going to be the constant, right? Doesn't matter what the constant is. Limit as x approaches 7 of 5 is 5. Right? The limit is always going to be the number, limit of a constant. Here's where it starts to get a little bit interesting. If you have a constant times a function, then it turns out you can actually factor the constant out, compute the limit of the function, and then multiply the constant afterwards. So that's just c times L. You can factor constants outside of limits. So if you ever have a limit and you have a bunch of things, you want to factor a number outside just to make things nicer and clean things up so you can figure something out, you're allowed to do this. And you can factor constants out of limits. Here's also something nice. Limits actually distribute across sums. So if you have the limit of a sum, it's actually the sum of the limits. Of course, sum is the general case. It would also work with minuses. Right? Limits distribute across sums. So if you ever wonder, if I'm adding up a bunch of things and I want to take the limit, can I just take the limit of each part? Yes. You can do that. Limits distribute across sums. Now here's something that's rare for one thing to have both times. but the limits also distribute across products. So if you have the limit of two functions multiplying each other, you can actually find the limits individually and then multiply them afterwards. And of course, that'll be like delta times. So this is x approaches a, this x approaches a. Now that's strange, in a good way, right? Not everything distributes across both things, right? Like powers, they don't distribute across sums, but they distribute across products. Limits distribute across both. You can distribute a limit across a sum or a product. It's really nice in that way. So, telling you works for products also implies this, but let me just be specific here. It also distributes across fractions. So if you have the limit of a fraction, you can actually take the limit of the top and the bottom individually. So that would be L over M. Now, of course, you can't divide by 0, so this is provided M is not 0. But if it's not 0, then you can actually distribute the limit across the division. Here's another nice thing. Limits can go inside powers. So if you have the limit of something and it's raised to a power, you can actually move the limit inside. Find the limit of the inside thing and then raise that to a power. So if you have the limit of a radical of something, you can actually take the limit of the thing inside the radical and just leave the radical on top, and that will be the answer. So they actually move inside of powers. So you can factor them in and out of powers. You can distribute them across sums. You can distribute across products. Here they usually mention any greater than 0 because they don't want you to have a negative power and it's 1 over and you get a division by 0, but it works generally. Just to make sure you don't divide by 0 at any point. So these are the properties of limits. In other words, limits are very algebraically nice, they're very algebraically forgiving. Chances are, if there's any algebraic manipulation you want to do with a limit, it's legal. It's kind of. So there are many things that aren't this nice, they aren't this forgiving. They'll work over in 3, but they won't work on 4, or vice versa. They'll work on 4, but they won't work on 3. So to distribute across both sums and products is actually rare, and it's nice when it happens, and it happens with limits. So when you're doing calculations, limits are actually nice to work with. So as long as you follow the previous rules, when you're doing computations and you want to simplify things, they're very nice to work with. So that's that. And now I think what I want to do is to move on. I think we're moving on into a different chapter. I think probably chapter 3. But I want to talk about attacking the finally attack the rate problem. So turns out now with limits in our arsenal, it makes attacking a problem that seems as daunting as the rate problem not so bad. So remember I told you calculus was about solving 2 problems, the rate problem and the area problem. This is one of the main reasons why we're here. But there's going to come a point where we need to actually make some kind of philosophical or computational leap. And in order to make that leap, we're actually going to need limits. So this was the main point. We were trying to figure this out, and we got to a point where we needed to make a certain leap, conceptual leap, and like, how can we actually logically, mathematically make that leap? So we went over here, we invented limits, we figure out how they work. Okay, all this stuff works out, it's really nice, I think we can do it now. So that's what we're going to do, we're going to attack the rate problem. So remember what the rate problem is, trying to figure out how fast something is moving. What thing, anything. A general method for figuring out how fast something changes. So let's start with a motivating example. So I'm going to talk through this kind of quickly, kind of hand waving, but never really gonna ask you to explain this, but it's nice for you to know where these things that we'll be talking about are coming from, how it kind of gets built up. So motivating example, suppose you're tracking an object moving at constant speed. Right? So something is moving, you're watching it, it doesn't seem to be speeding up or slowing down, it's just steadily moving at constant speed. Maybe you're like Newton, watching the planet go across the sky, right? It's just moving, right? And you're tracking this, you want to be able to predict where is this object going to be, how fast is it going to go from this point to that point, right? That is your goal. So you track its distance traveled over time. Now this is a very simple model. Almost nothing actually behaves like this. But let's say you're actually tracking it and you did it on a graph. Let's say you're plotting distance versus time. And just to be suggestive, let's say this is in hours, miles, and this is in hours. So at a certain position in the sky, you consider that to be the origin. Okay, that's position 0. Okay? And its time equals 0. And just start the stopwatch. And so now you're measuring how far this thing is traveling over some period of time. Let's say after 3 hours, right? You're watching this thing for 3 hours. You notice that in that time, it covered a distance of 150 miles. Very long. Now it's moving steadily, so you kind of expect if you were to track how fast it's moving, and you plot this at any point, like after 1 hour, it'll lie on this line. After 2 hours, it'll lie on this line. It all moves very steadily, so we get a straight line out of it. Okay. So now, I'm going to ask a question that might seem like it's coming out of nowhere, but there's a point. Question. What is the slope of this line? Well, what is the slope of the line? How do you find the slope of this? Yeah?
You would do 150 minus 0 is in the denominator, and
Right.
then
So it's y2 minus y1 over x2 minus x1, x1. And these are the y values here. So 150 and 0, so that's y2, y1. And x2, x1. So that leaves you with 50. Okay? Where are you going with this? Okay, follow-up question. Interpret that number. What do you think that 50 means? 50 what? Yeah? Miles per hour. Now, of course, I wanted to make the units very suggestive, but this 150 isn't just a random 150. It's measuring a 50 miles. It's measuring 150 on the axis that's measuring miles. So this here is 0 miles. And the 3 here is not just some random 3, it's actually measuring time in hours. So this here is saying 3 hours, and this here is saying 0 hours. So in other words, the units here are miles divided by hours. In other words, miles per hour. So the 50 is actually 50 miles per hour. In other words, it's the speed of the object. The slope will actually tell you how fast the thing is moving. But hey, figuring out how fast the thing is moving is the whole point of the exercise, isn't it? So, there's seems to be a connection. Between slope and rate of change. How fast is it changing its position or whatever? And so that's where the wheels started turning, right? In a very simplistic case, right? Like very few things are gonna move this steady. But if it did, the slope is actually gonna tell me how fast the thing is traveling. And so now there's another follow-up question. Can we generalize this idea? And the answer to that question is surprisingly, no, we can't, so I guess we're done here. Sorry. No, the answer is yes, we can. That's why we're here, that's why calculus is a thing. Turns out that in solving the rate problem comes down to actually generalizing this idea that I just mentioned. This is the very simplistic, basic case. And what we want to do is we want to apply this case to more complicated examples. Like what if it wasn't a straight line? What if it was just some crazy function? Could I still do the same kind of examination? And the answer is yes, some of the times. And we're going to talk about when would this examination not work out in your favor. But it turns out there are a lot of times when this kind of examination is in your favor. And here's how. Well, it all comes down to slope. Now we know about how measuring a slope can work. And slope of a line, only thing we know so far. Right? And for that, we need 2 points. So let's kind of set the stage here. So let's say I'm now trying to graduate to bigger, better things, and there's some curved function that I actually care about measuring rates of change or figuring out how fast it's moving. Now, I don't really know how to do this at the moment, because that's a very big problem. But I do know if there was a straight line, I would know how to handle it, and with 2 points. So what we do is, we start with the average rate of change. That was something that we defined a couple classes ago. So we pick 2 points of interest on this function. There's a straight line that connects them. Now, this guy is called the secant line. I think we mentioned that before. And the slope of the secant line can be interpreted, in fact I think we actually did this, as the average rate of change. So if someone were to ask me, how fast is this thing moving on average over this time window, which might be a very large time, like 3 hours, I can answer that question, and we could have answered that for a long time actually, right? On how fast on average is it moving, right? We can answer that question. You just create a secant line, use those 2 points to use the slope formula, and you're fine. And so if I had a distance, I don't want to do that now. If I had this distance here, x, and this distance here, call it x plus h. So it's a familiar chart that I'm setting up. So if I had a time window or a window of something else, it doesn't have to be time on this axis, that has a distance of h units, and this here is my function f of x. Then the corresponding output here is going to be f of x. Corresponding output here is going to be f of x plus h. And we could determine from that average rate of change is going to be equal to y2 minus y1 over x2 minus x1. That gave us the average rate of change. The difference quotient gave us the average rate of change. Now, here's what we want to do. We want to be able to do this at any instant, right? So the trick is not to tell me over some huge time window how fast we're moving on average, how fast we're moving right now at this point, right? That's going to allow me to discover how fast is this object moving over time. I can know at this time how fast we're going, at that time how fast we're going, at this time how fast we're going. We want to be able to point at any point in time and say, how fast are we moving right now, right? So this means we want something that's called instantaneous rate of change. And what that means is we need to be able to find a slope or something analogous to it at a single point. Let's say x, right? So let's say I don't care about how fast it's moving on average. How fast is it moving when I'm right here specifically at that point? Now I would want to be able to measure a slope of that because there's a connection between slope and rate of change. How can I actually measure a slope at one point? You need 2 points to create a slope, don't you? y2 minus y1 over x2 minus x1. You need 2 points. So the idea to get the slope through 1 point is going to be the following. So here's our point of interest. So call that x, and of course the output here is f of x. So that's our point of interest, okay? So now the idea is start with another point as well. Let's say some random guy over here. And we can consider the line connecting them. But here's what we do. Then move the second point closer to the first. So here's the idea that we want to get to happen. I care about this point, I need 2 points. The idea here is actually close this window. If this point occurs at x plus h, actually close the distance h between these two. So I want to take this point and I want to move it closer and closer to that point until I'm in a scenario where it's like these 2 points are right beside each other. Where it's like the 2 points are actually like 1 point, right? So computationally, algebraically, it's 2 points, but in reality, it's kind of like they're going into 1 point. In fact, we want the distance h to go to, well, essentially 0. If I can make the distance between these 2 points 0, I'm able to use my slope formula while at the same time literally creating the window I'm looking at, shave it down to an instant. And so now you're like, well, if only there was a way for us to get this guy to move closer to 0. And that's what a limit is about, isn't it? Limit allows you to approach something. To get something to move closer and closer to something, to inch closer and closer to it. What is a tool that we have for that? Well, at one point it didn't exist, and then at another point we're like, let's invent something that we're going to call limits. It's going to allow us to inch closer to things without actually even getting there, because technically we need 2 separate points, but we want it to be super close, like it's 1 point. how do we develop this idea of being super close? What does that even mean? And they started asking all these questions, and they came up with the idea of a limit. And then they researched the limit, they find out how they would have to work, all the calculations, everything we've actually been going through over the past week and a half or so. All of that we figured out on the fly, but the whole point of having to figure out all of that was to be able to do this, to solve this problem. So the idea is, as we keep inching this point closer and closer and closer and closer and closer, we were creating a bunch of lines connecting those 2 points. And the lines kept going to a point where eventually this point is going to be so close to beside that point, to the point where, I mean, you're overusing the word point, there'll be like a single line that is passing through those 2 points. But, you know, if you kind of think about it, it's almost like there's that little one line passing through 1 point, right? Because the 2 points are so close together. The distance between them is 0. They're like right beside each other. Drawing a line between those 2 points is kind of like drawing a line between that 1 point. That line is what we call the tangent line. So it turns out by closing this distance, we can go from a secant line and we can actually make it converge, as we would say, to something called a tangent line. That tangent line is a straight line that passes through a single point on the curve, so that when you zoom in, it looks pretty much like the curve. We'll talk about that a little bit more later. But the idea here is now we're able to measure the slope at a single point. And we can use limits. That was the whole point. So the slope of the secant line, well, that was f of x plus h minus f of x all over h. And so this would mean that the slope of the tangent line, this line that I want to create here, is just going to be us starting out with that slope. So it's originally the slope of this guy, but I move that slope closer to the slope of the red line by actually moving the points closer together. And I do that by closing the distance between them by throwing in a limit, h approaches 0. So I can have 2 separate points at a distance h from each other. I can close the distance to 0, and now it's like those 2 points are now 1. And me drawing a straight line through those 2 points is like me drawing a straight line through 1 point. And measuring the slope of that line is like measuring the slope through a single point, the slope through an instant. That gives me this idea. And that's pretty much it. That actually helps us solve the rate problem, believe it or not. I mean, we're going to do a lot of examples where you're going to see how we're going to use this, but that was the whole idea. And we'll stop there for now. Next time what I'm going to do, we're going to package this very nicely. I'm going to give you some notation to talk about this. But that's the idea. That's the solution to the rate problem. And we'll spend a lot of time on applications seeing how this works, but that starts next time. I'll see you guys on Friday.